Hi, this is going to be the last unit on general reinforcement learning before we move on to AlphaGo and AlphaZero. But in some sense, might be the most interesting part of the general discussion of reinforcement learning. Let's review where we were with the reinforce algorithm. So the reinforce algorithm is a policy gradient algorithm, and the rest of this unit is going to continue to be about policy gradient. So in policy gradient, our model is modeling the actual policy. And we're interested in optimizing the performance of the policy. So we're interested in the gradient with respect to the policy parameters of the reward. And the reinforce algorithm says that's equal to the expectation over behaving according to our current policy of the gradient of this log of a sum over time and future times of the gradient of the policy of the log policy at the first time and the reward at the later time. Okay. Now, last time I said that the reinforce algorithm often comes up when you're training some loss function that's a function of discrete actions, like the blue score. I forgot to say, and I should have said, that that's generally considered a bad idea if there's any alternative. If you're not forced to optimizing choices of discrete actions directly through some loss that's a function of the discrete actions, because you lose differentiability. And the fundamental problem there is that reinforce will take a long time to converge. You have to use a very small learning rate. Nonetheless, sometimes, like in games, in Go, you fundamentally have discrete actions and you fundamentally want to win the game. And winning the game is a function of your discrete actions. So we're going to continue to talk about that case. Okay, so here's where we were. Now, what we're going to do in this unit is discuss various ways of reducing this high variance, making this thing converge more quickly. So the first thing we're going to focus on, so we've got two T's here. This is the sum over a first time and a second time. At the first time, we're looking at an action that was selected at that time, and we're looking at the gradient of the log probability of that action. And then we've got a reward that's coming from some later time. Now, this is going to have high variance due to the fact that this reward is a random variable. And this reward is going to depend on actions that happen after, in between these two times. So there's a lot of variance due to this reward. So the first thing we're going to look at is trying to greatly reduce that. And that leads to actor-critic methods. And then the next thing we're going to look at is there's also a variance in this due to the fact that this state that you're at the first time is a random variable, right? Because you're behaving in some random way and you reach that state. And there's a lot of variance due to the selection of this state. And if you focus on that, you come up with this notion of advantage, and you get an advantage actor-critic algorithm. This is going to be clear later. I'm just trying to summarize what we're going to cover. And finally, if we use asynchronous methods, this was an alternative to the replay buffer, if you remember from the earlier units. You come to asynchronous advantage actor-critic methods, or A3C, which was something that came out of DeepMind as a refinement and improvement on DQN, which we did the last time. So that's a summary of what we're going to do in this unit. So the first thing I want to do is talk about reducing this variance due to the random reward at the later time. And we wrote a paper on this. I was at AT&T, and we submitted a paper to NeurIPS in 2000. And it was this bizarre experience where we submitted this paper, and then we saw another submission to the same conference that was the same paper. Theorem 1 was the same, Theorem 2 was the same. It was this creepy thing. So our paper was Policy Gradient Methods for Reinforcement Learning. Rich Sutton was big at that time into reinforcement learning. And he came to me and said, boy, if we could just prove this theorem, it would be important. And I did not understand reinforcement learning. So I didn't understand the significance of the theorem, but I said, okay, I think I can prove that. Anyway, so these two papers are essentially identical. We now have, way more citations. So what's the difference between these two that got us more citations? Well, this paper was wrapped in very sophisticated mathematics. It talked about the tangent space and very sophisticated mathematics, which made it very difficult to read. So if you want to get a lot of citations, please don't demonstrate how smart you are by burying the content in very sophisticated mathematics that makes it very inaccessible for most readers. You're likely to be, overshadowed by somebody who presents it more accessibly. Anyway, so this is what we're trying to do. We're trying to reduce the variance over RT over this later reward. So what we're going to do is I'm going to take this is the reinforce algorithm. It's summing over 2 times. And I'm going to, this term depends on the first time, and this term depends on the second time. So I'm just going to take this sum over the second time and move it in. So I've got a sum over the first time, and this is the sum over the second time. And I can move the expectation. The first thing is just the expectation over the first 2 variables. I can move the expectation into this second term, the expectation over the second reward. And this sum can be written as a Q function. This is equal to a Q function. It's the expectation of the reward after this time, or at this time and later. And what's happening here is this thing has huge variance due to the random unrolling of this history. This thing is taking all of that variance into account and just looking at the expectation. Now, how can I do that? Well, I do that by training now 2 networks. I train the policy network, and I also train a Q function network. And then by training this Q function network to approximate this part, I get rid of the variance due to this random variable that's happening later in time. Right, so I've just said this. The point is that we can now train a Q function along with the policy. So we're still doing policy gradient. We still have the policy network, but now we have 2 networks, and this reduces the variance. So this produces the Actor-Critic algorithm, right? The Actor-Critic algorithm, in the Actor-Critic algorithm, the policy is viewed as the actor. The policy acts, chooses actions, and this is the critic. This says how good your action is using a Q function. So now we've got 2 networks, and we're going to have to train them both, right? So what we can do is we can sample an episode. We're sampling an episode from the policy, and what we're going to do is train both. So we're going to update phi by a gradient that's looking at the gradient in the policy gradient component. So here I'm using the same phi, but the intuition is that there's a part of this phi that's defining the policy and a part of this phi that's defining the Q function. And maybe there are shared parameters, but now there are 2 gradients. There's the standard reinforcement learning gradient from the reinforce algorithm. That's this. It's looking at the gradient. It's looking at the gradient. The gradient of the policy, the effect of the gradient in the policy, assuming that this Q function is reasonably accurate. But we also want the Q function to be accurate. So we also have to take what's essentially a Bellman error to train the Q function. So we also take a gradient with respect to the difference between what the Q function says. And remember, we've sampled a random episode. So if we've sampled an episode, we have this sum over T prime, and we can take the gradient we can take the difference between these 2 squared as a kind of Bellman error that trains this function. Okay, so now we're training 2 networks. Okay, now we're going to get to the next part, the advantage part. So what's happening here is that in this expectation, there's also a lot of variance due to the random choice of this state. And it turns out we can reduce the variance due to the random choice of this state by introducing yet another network, a value network. So what I'm going to do is I'm going to take the Q value, and I'm going to subtract a value function that's just a function of the state. And the idea is that if this is an average over the actions of this, that if I subtract the mean, the variance will go down, right? If I have any random variable, the variance of the variance is the value minus the mean squared. So I'm taking the value minus the mean squared. That's the intuition. And that's going to have less variation than the value itself, because the value itself is going to have a variation that includes the variation of the mean, the average over the state. So I want this value function to be an expectation over A drawn from the policy of the Q value of A. And this is called the advantage. It's the advantage of using A rather than whatever the policy says, rather than sort of the average over actions. The policy could be wrong. There could be some action that's better than the one the policy is picking. So now we have to train, first there's a proof that this equality is actually true, right? I first want to prove that I can add this term, and I still, if this is defined to be the true Q function, and this is defined to be the true value function, this equality still holds with equality. Okay, so the proof says you take any function of states, like the value function is just a function of states, but as long as it's a function of states and not looking at the average over action, and I look at the expectation of this term times this value function, this expectation involves a sum over A of drawing A according to the policy times this term times this function that does not depend on A, right? So I can pull this function, I can pull this value out of the sum over A. I did this in the, sorry, I apologize. I did the two, that's coming in the next step. The first step transition here is to take this gradient. This gradient is 1 over the policy times the gradient of the policy. That 1 over the policy cancels this. Apologies for not following the slide. Take the gradient of this, that becomes 1 over the policy probability times the gradient of the gradient of the policy probability. That cancels and we get this expression. Now this term can be brought out of the sum because this does not depend on A. And what I'm left with is the gradient of the sum over AT of the probability. Well, the sum over AT of the probability is just 1, independent of the policy, for any policy. So we get that the gradient is 0. So the gradient due to the bottom line is the gradient due to the addition of this term is not altered. This term does not alter the gradient. Okay, now we've got 3 networks that we have to train. So we've got the policy gradient. So we've got a gradient term due to the policy gradient. Here we're using the advantage, which is helping us reduce variance. We've got the training of the Q function, and we've got the training of the value function. The value function wants to be the average over the draw of A of the Q function. And that's exactly what minimizes this squared difference. So now we have these 3 gradient components. We've got these 3, potentially 3 networks. And so here's a paper that appeared in 2016. This is the A3C paper from DeepMind. So they're going to now add add an asynchronous adjective. So it's an asynchronous advantage actor critic, A3C. And so this is a description of the asynchronous method. So the asynchronous method replaces the replay buffer to make things more stable. You've got a bunch of asynchronous actors, each operating at a different fee. So you've got a mixture of different parameter settings that the agents, these asynchronous agents, are working with. So it makes it sort of, each agent is sort of more off policy. And then you've got a rollout Bellman error. I'm not going to go through the details of this. Okay, what are the issues of policy gradients, of the policy gradient methods? They're sort of fundamentally exploiting or relying on non-determinism's exploration in the policy. It's important that the policies be stochastic. So that the gradients are meaningful when you take the policy gradient. But in practice, the optimal policy is often deterministic, right? There's often one action that gives the best expected reward. So you've got this tension between wanting exploration and having the optimal policy actually be deterministic. In practice, what people do is they force a random action. They just force a random action to get exploration some fraction of the time. Another thing that's strange is that these algorithms are trained with discounted reward. But if you think about a game like that breakout game or one of these other games, it's really sort of episodic, or at least the game lasts much longer than the discount rate is looking into the future. The discount, the weighting tends to go to zero long before the game is actually over in these Atari games. And that's presumably because when you take an action, it's primarily influencing the states that are near you in time. If your policy has a mixing time, right? If the effect of that action is sort of lost in the future, that's probably why you only want to take the rewards in a sort of neighborhood near the place where the action was taken. But it would be nice if that theory was somehow explicit, right? It'd be nice if the theorems talked about the mixing time or something. At the end of this unit, I just want to point out that everything we've said in this unit involves discrete actions. If the reward is continuous and the actions themselves are continuous, so how do we get continuous actions? Well, the idea is in robotic control, if I'm moving my hand, there's a continuous, there are continuous signals being sent to my actuators. And what actually happens is actually a continuous function of the signals of the differentiable continuous signals being sent to my actuators. So if the reward's continuous and the action is continuous, I can take a deterministic policy and simply differentiate the reward with respect to the continuous actions and back propagate that into my network. So for robotic control, you don't have to go through all the processes that I just talked about. And I just want to show, just because it's fun, I'm going to show some share. Sorry. I just want to show some videos that came out of DeepMind of optimizing robotic behavior. So let's just look at these. So this is talking about what sensors it has and how many degrees of freedom it has. And here we're just optimizing I think we're just optimizing forward progress, doing continuous gradient descent on the control of this robot. And this was fun to watch. I mean, this is parkour, which is always fun. This has a vestibular sensor. That's your inner ear. So it has like a gyroscope that's detecting its physical motion. I think for me, here's a humanoid. Yeah, I don't know what this is, right? For me, these simulations are interesting because if you have real physical robots, you're so limited by the sort of very primitive state of our actual robotics, the effectors and the sensors. Here in these simulations, that problem sort of goes away. I mean, you have a sim to real problem, in that the simulations don't correspond much to reality, but you've sort of assumed away the control and sensing issues, and you can really focus on the learning, the optimization algorithm. So in terms of understanding optimization, I find the simulations more interesting. And it's clear that that whatever they're doing here has a lot of room for improvement, right? What is this? And we'll see things later on that are clearly show that there's lots of room for improvement, that there's a long way to go in these simulations. You would think that you could do really well in simulation. And in some sense, this is doing really well, right? It's actually doing pretty well on the objective function. It just looks bad. I heard a story about OpenAI. Elon Musk funded OpenAI in the beginning, and he backed out eventually. And I was talking to somebody who had worked there and who had witnessed Elon Musk coming in and looking at some of the videos that we're seeing now, where the robot was doing really embarrassing things. It just looked embarrassing. Just a minute. There's a next video I'm going to show. So this is just more from DeepMind. So let me finish the story. So OpenAI was funded by Elon Musk, and Elon Musk came in to watch. He looked at some of these videos, and he's very into doing things that excite the public, that are dramatic, that are impressive. And he looked at some of these videos of humanoid robotic motion and said, why are you guys wasting my money? So I don't know if that's why he backed out, but he did eventually back out of funding OpenAI. This one is unfortunately a little suggestive. This is called the swimmer. So again, this is all differentiable actions. So you're just doing gradient descent on the reward. You're taking the gradient of the reward with respect to the differentiable actions. We're seeing random motion and then after training. Okay, this part is I find the most fun. Okay, so this is, we've got the thing to stand up. Its arms are weird, but it stood up. So I think this is being trained on some objective function. Maybe the walk is not trying to move as fast as possible. Here we're trying to move as fast as possible. What's interesting is you get these different local optima, right? These are really different motions, but they're all traveling along at a pretty good rate. This is my favorite. Backflips with a big jump, jump, backflip, jump. And here's motion capture. I don't know why they motion captured dance. I would have motion captured just real walking and running to see how different they are from what has been learned. Okay, I'm going to stop this. All right. Okay. Thanks, everybody. Next time we'll get to AlphaGo and AlphaZero. Thanks.